Who was the guy that came up with the whole, or used at least, the first to use radiometric dating to figure out an estimate for the age of the Earth? Arthur Holmes. Very good. Good memory. We're going to kind of sort of dabble. Now listen, the algebraic equation for radiometric dating is like T equals, and you need the decay constant for whatever decay series you're using, and you put it all into this beautiful algebraic equation. But how many of you are experts in algebra at this point? Like college level algebra? Okay. I have a feeling that if I showed you this the formula, I should have it up by the way, but I don't, you'd be like, no thanks. Because there's like no numbers in it at all. This is, by the way, advanced placement nuclear physics that he's teaching, all right?
The original activity is just lambda times n naught, and everybody knows that activity
I love that. He's like, everybody knows.
M naught, n naught times e to the minus lambda t, because the definition of activity is, well, I think they said that activity is lambda times n, and this is n at any moment in time. So this is a reasonable statement, and then we can just solve this. Well, ultimately, I'm trying to solve this sucker for t. Watch this. I'm going to say r over r naught in e to the negative lambda t.
What?
A little bit and whisper.
What the heck is that?
I'm trying to get the natural log. It's the only way.
He's attacking with the natural log. Pay attention.
This ratio r over r naught. Can we just get a
Huh? Yeah, you guys should start copying this down. The first row, there's different ways you could build this. The way I always build it is number of half-lives gone by. Number of half-lives gone by is your first column title. Do we remember what a half-life is?
What it takes to...
Neutrons or protons to become half of a
Well, you guys are bouncing kind of around it. It is a length of time. Half of a parent isotope sample to decay into its daughter isotope. So we've got multiple decay series, all right? So the decay series we're going to use for today, we're just easing into this. We're going to use carbon 14 to nitrogen 14 decay series. So the parent isotope is carbon 14, the daughter isotope of beta decay, by the way, is what's going on here, would be nitrogen 14. So parent, daughter. Good? All right. The half-life for carbon 14 is 5,730 years. None of this, by the way, will be things that you have to memorize. We're building a chart. You're going to have the chart to use, okay? So if 0 half-lives have gone by, how much of the parent isotope would have decayed? None. So our fraction of parent, if I can spell parent, that'd be good, to total, which is parent plus daughter isotopes, would be what? None of it has decayed. So of all of the parent plus daughter isotopes, how many of them would be parents? All of them, right? None of them had time to decay. So our fraction would be 1 over 1 or just 1. Yes? If you're not tracking yet, that's okay. Most of you are just trying to copy down. Keep up with the copying down. So that's going to be our first real row. And if no half-lives have gone by, what would be the estimated age of the sample? Huh? if no periods of time have gone by, no decay has happened, all of the isotopes are still parent isotopes, how much time would have gone by? 0. Or so little that you can't use radiometric dating for it. Does that make sense? So if it's so fresh, like for example, for carbon-14 to nitrogen-14 decay series, the usable range is like 100 years out to maybe 50,000 years, depending on how sensitive the equipment is. So if it's less than 100 years old, you really can't determine the age because it hasn't had enough time to start decaying yet. Does that make sense? Right. And then after 50, or I think a more accurate number I've seen is 57,000 years, but you're really pushing it because there's not going to be much carbon-14 left. The fraction is going to be so small of what's left that it'd be hard to even find any. Okay. After one half-life has gone by, how much parent isotope would be left in a sample? After one half-life has gone by, a half. Good. So 1 out of every 2 of the originally parent isotopes are still parent isotopes. Okay? And that, of course, in a decimal form would be 0.5. Okay? Half of the material is still the parent isotope. And what would the age of the sample be at that point? After one half-life, what?
5,700.
Yeah, because that's the half-life of it, right? Good. Each time.
So the second one, the fraction would be 1/4.
Yes.
Oh, okay. Yeah, I got you now.
Or as a decimal, 0.25. Because half of a whole is a half. Half of a half is a quarter. What's half of a quarter? An eighth. How many years would have gone by after 2 half-lives?
Probably like 17,000-ish.
How about you just add 5,730?
So I don't know.
Wait, that doesn't make any sense.
Nope. Nope.
Yeah, you have calculator, right?
17,000.
Nope.
What?
5,730 plus 5,730.
You're talking about the third one.
Guys, let's just do the math here. It's like 17,000 and...
No!
It's 11,400.
There you go. 11,000 what?
Third one.
11,000 what?
460.
460. Okay. You can go 3 times the half-life and 4 times the half-life. You just can't double it each time. Does that make sense? Or you could just add another 5,730.
Oh, so
I got
confused. I thought you were talking about
So what's for the third one then?
17,190.
And then 4? That's fine. I'm patient.
22,000. 920.
920. Okay.
You do that all in your head.
Oof.
Apparently can't do math.
Oh, and our fraction in the middle would be what?
1/16 and yeah, I don't know.
0.016. Excuse me. 0.0625. Is that right?
Yeah, I had that.
Whew. All right, is everybody there on the chart? So did that exercise your mind just setting the chart up?
I think that's all we got.
No, that's not all we got to do. So now we're going to use it. All right. So can I erase the usable range? Get this out of our way. All right. So let's paint a picture here, like set up a scenario. Let's say there's an archaeologist that is working, and they find an ancient campsite, and they find charcoal or leftover remains from the wood or from maybe a chicken bone or something like that. For radiocarbon dating, it has to have been something that was alive. Okay, Okay, so carbon dating is only used to date things that were formerly alive. Okay, gotta be dead. You can't date like, well, you said 100 to 57 or 50,000 years is the usable range. What if it's a giant tree that's over 100? We know it's over 100 years old. Can we use carbon dating to date it? No, because it's still alive. It has to be dead for over 100 years. Does that make sense? It had to have been alive. Yes, it can't be a rock because the rock wasn't alive. All right, so somebody, let's say, so you get a sample, they run it through a spectrometer. So the sample has a certain number of parent isotopes left in it, and it has a certain number of daughter isotopes left in it. Follow me? All right, so you get the number, you put it in a fraction. We're just gonna make up a fraction, okay? So somebody give me a number between 1 and 10. 10, all right. Somebody give me a number between 10 and 30.
30.
Okay, can we reduce that further?
Yeah.
1/3. All right, so let's say our fraction was about 1/3 of the sample that was parent isotope is still parent isotope. Tracking?
Yeah.
All right, so this, again, to make it more clear, this is 1/3 is still the parent isotope, and the whole here is parent plus daughter. Okay, that's your fraction. What we do is we say, where does this fall on the chart? Where does 1/3 fit into the chart?
Right between 1 and 2.
Between 1 and 2?
Oh yeah.
Because 1/3 is less than a half, but more than a quarter, right? So let's try this. Let's take, let me ask you a question first. Is 1/3 directly between 1/2 and 1/4? You're shaking your head no.
No, I agree.
Who says it is? I mean, 2, 3, 4 are right there even, right?
Well, there could also be something in between 0.5 and 0.25.
Yeah, you're using percentages, right? So you're like, not exactly, right? So, but let's prove it with optics. Let's look at it. Let's turn this in to a timeline / number line. So we have the half and the quarter. We're going to turn them on their side and we're going to open it up, okay? So we're going to have 1/4 over here. Oops, 1/2. I like having a half over here. And 1/4 over here. And how much time would have gone by at a half?
730 years.
Yep, so this is we've got our number line side and we have our timeline side. So this would be 11,460. And if it were true that it'd be right in the middle, well, you'd expect this to be right there in the middle. Okay? Let's see if that happens. We need, by the way, to do a true comparison, oh my heavens, to get a common denominator. What is the common denominator between 3, 2, and 4? Hello? What's the common denominator? 12. All right, so 1/3 becomes what twelfths? 4 twelfths. And a half becomes 6 twelfths. And 1/4 becomes, look at you all are just on it. How many of you all in class are like, wow, they got that really fast. That creeps me out. Okay, but you get it, right? So you're maybe you're just a split second behind them, I'm sure. All right. Now, how many increments between what's the difference between 6 and 3?
3.
3. So couldn't I just put 2 dashes up here
Yeah, probably around there.
to cut it up into 3 pieces? You're probably like, what are you doing? Okay, just hang with me here. So we have 3 increments now. This one would be 4 twelfths. This one would be 5 twelfths, right? And our sample would go right here, yes? Okay. How much time between a half and a quarter with carbon dating?
Oh, a good amount.
5,730 years. Good. And we're going to divide that by 1, 2, 3 increments to see how much time is in each of those. Go ahead and do the math. Did you do that in your head? Seriously? Somebody check it. If you get that right, I'm going to be like, wow, that's pretty good in your head. Somebody with a calculator, go ahead and do that.
I think I'm pretty close. He's definitely right.
5730 divided by 3.
I think it's 460.
1,910.
1,910.
You got it right, Craig.
Is that what you said?
I was off by 8.
Oh, well, you stink then. So what that means is each one of these increments is 1,910 years long, right? Our sample is just one increment away from this. So couldn't we subtract that from that to get the age of our sample?
Yeah.
So take 11,460 years minus 1,910. 11,460 minus 1,910.
9,450.
Are you guessing or
She's definitely guessing.
what'd you get, 9550? Good job. Well, I thought maybe you were doing it in your head, so that's impressive. Okay, good. All right, so our sample, look, if you had 1/3 of the parent isotope left and you're using carbon-14 dating, that means our sample is 9,550 years old. You know, give or take a couple. You probably have a rounding error here or there. As long as it's minor, you're good. Somebody give me a number between 1 and 10. 8. I heard 8. I heard 7 as well, but I heard 8 first. Okay? So 8 parent isotopes remaining in our sample out of a total of, somebody give me a number between 24 and 40.
29.
I heard 20. 26. I heard 26. I was waiting for a number that we might be able to like reduce because I don't like having to, the common denominator thing could get really big really fast. All right. So 8/26. Can we reduce that?
Yeah, like 4.
So it'd be 4
Nothing goes in the
4/13. 13 twice. If it's an even number, generally, and something could go into it, right? All right. So 4/13. Where does that go in there?
Right between, well, let me figure it out real quick.
Well, 4/12
I think
is a third.
16.
Huh?
Right between 3 and 4.
Between 3 and 4?
Yeah, I think.
You think it's that small? What's another way we could check? I think it's just barely less than a third, which means it would still be between a half and a quarter.
Oh, would it?
Yeah, I think it's here. But we can check it another way. Divide 4 by 13.
It'd be 1.
Oh, it's like 3.146.
3.25.
1 3
No, it's like
it'd be a decimal.
It's like
4 divided by 13. Use the calculator. 0.301. All right. So 0.301 does go 7 does go right there again. So I was right.
Why are you saying like you could change it to 2 and actually never mind, you got it wrong.
Okay. So I was right. I love that. Because it doesn't always happen that way. Sometimes I am wrong, and that's fine too. All right, so it fits there. So we're going to have the same timeline that we had last time. So we have our half, we have our quarter, we have our 11,460 years, we have our 5,730 years. We want to find a common denominator between 13, 4, and 2. We know 26 doesn't work because 4 doesn't go into 26 evenly. What if we doubled it? What if we went to 52? Does 4 go into 52? 52 divided by 4?
Yeah.
Yes. So our common denominator is going to be 52. What is a quarter of 52? Somebody just said it. 13.
13.
What?
Wouldn't 0.307 go between 2 and 3 because 0.307 is greater than 0.25?
Yes. Greater than, less than. So 0.25, 0.3 would be greater than. Does that make sense? Okay, cool. And then a half of 52 is what?
16. I mean, not 16.
26. All right. And 4/13. So if we did, to go from 50, what? We went from 13 to 52, we had to multiply it by 4, right?
Yeah.
So what's 4 times 4?
16.
16. So 16 50 seconds. And we can confirm that we're between the correct ones because 16 goes between 26 and 13. Whew. Okay. How many increments between 13 and 26? What's the difference?
Like probably
13. Don't say probably. 13 plus 13 is 26, yes? So how many dashes to make 13 increments?
11.
12. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. Totally not equal in lengths, but it works. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 increments, yes? Fantastic. What is 5,730 years, which is the length of our timeline in years, divided by 13? Yeah. What is 5,730 divided by 13? 440.77. All right, so what does that mean? Each of these increments is almost 441 years long. Yes? And our sample would be, this is right here, so 14, 15, 16. It's right there. So 1, 2, 3 increments short of that. So we'd take 11, first of all, take this times 3, right?
Okay.
So 441 times 3 is?
1,322.
So this is from here to here, yes? So what is 11,460 minus 1322?
You're off by one. You're off by one number.
Because of rounding? Cool.
This says 1,323.
Okay, probably due to rounding.
God.
So 10,138 years old. Our chicken bone or our charcoal or whatever it is, 10,138 years old. Whew. Does that make sense?
Oh yeah.
Okay. So we've done a couple of examples. Hopefully you're like kind of sort of get, how many of y'all are like, okay, this makes sense?
No, not really.
Not yet? Okay. What? Now, you got to tell me what part of it do you think is that you're struggling with? We've only done 2 examples.
Really just like the multiplying stuff.
Oh, just basic math?
No, not the basic math, just like setting it up.
The setting it up, like with the chart?
Yeah, you know. Like getting in between 1 and 2 and all that.
Oh, so the comparative fractions.
Yeah, stuff like that.
Okay. Let's do another one. How about, I'll give you the fraction.
What about 2? Oh, you did.
What might you try to do first with that fraction?
Divide.
It goes into 1/4.
Ah, so it simplifies to 1/4. So what's the age of the sample?
11,046.
Oh, we're done. That was easy.
60.
So we're done.
No.
Guys, once you simplify this and realize that it's a fraction that's on the chart, you don't have to do anything else. 1/4 doesn't go in between one of these. It is one of these. So your sample with that fraction is 11,460 years old. Done. Okay? Huh? For that one, that's it. Because all you were just using was the chart.
Okay.
It was on the chart. Huh?
You sound so sarcastic.
I'm not being.
I know, but you sound good.
I get that. All right. Shh. So how about that one instead? We'll do that one instead. 17/50ths.
It doesn't simplify to the chart. Nope.
Oh no. So you'll have to do what?
I have to find out what it's simplified.
Where it fits in the chart, right?
It's 1/10.
Well, it's 1/10.
After you find where it fits in the chart.
But like it's somewhere. Because it's 1 or
All right. Shh. The question is, how do I find where the fraction of our sample fits in the chart? Well, what's half of 50?
25.
25. That's less than half. So here's half. We know it's less than half. What's half of 25?
I don't know, like
12.5. 12.5 then would be a quarter. Is 17 bigger or smaller than 12.5? Bigger. So we know it's less than half and more than a quarter. So our fraction fits in between those two. Everybody got that? All right, now we're going to go ahead and make our number line. We're going to have a quarter on this side, which means the sample at this point would be 11,460 years old. All right, we'll back up. All right, so we would know that the common denominator had to be at least 50, right? Because 50 has to go into it. It can go into itself. Can 4 go into 50? No. 2 can 25 times, but 4 can't. So what we do next is we just take that, what the least that it can be, and double it. So we say 50 goes to 100. Can 4 go into 100?
Yes.
How many times?
50.
25 times, right? All right, so if we make this hundredths, we had to multiply 50 by 2 to get it to 100. So now we have to do the same to 17. What is that? 34. Now we're going to take half and represent it as hundredths. How many hundredths? What's half of 100?
50.
Isn't that the same as a half?
Yes.
Yeah. What's a quarter of 100?
50 divided by 2.
All right, good. There we go. Now, from 25 to 50, how many increments will we have?
12. 25.
25. 50 minus 25 is 25. So, to get 25 chunks of time on our number line or timeline, we'll need to put 24 lines in between the 2 lines that are already on there, right? So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. They don't line up. They're not perfect. It's okay. It's okay. It's okay. So now we have 25 increments. All right? Ours is 34 100ths. So we count 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Our sample goes right there on our number line, okay? Now, our sample is how far from 25?
1, 2, 3, 4, 5.
What's 34 minus 25? 9. Good. So we have 9 increments to go to here. All right? Shh. How much time is each of those 25 increments?
1.
Yes.
How much time, how many years are in each of those 25 increments? We divided 5,730 by 25, didn't we?
Yeah.
So it's 25.
So do that.
Wait.
Give me a second.
5,730 years, which is 1 half-life for carbon-14.
0.004.
Say again. Say again.
0.0043663.
0. So not even a year?
229.2.
229.2?
Yeah, that's what I got.
The majority.
229.
Did you do 20?
Wow. All right. Let's just round it down to 229. All right? So each of the increments is 229 years. We just said there's 9 increments from our sample to 11,460 years old. So we're going to take 229 times the 9, and what do we get? 2,000 what?
2062.8.
2063.
2.
0.8, so I'll round. All right, so from here over to here is 2,063 years. Okay? You don't understand? Let me walk you through it. So we had our number line that we took out of our chart. Follow me? We got our common denominator, so we're all in 100ths. From 25 to 50 is 25. So we took the 5,730 years, divided it by 25. So each one of these is 229 years. And then I said we're 9 away from this age. So we multiplied each increment by 9. So now we know it's 2,063 years here. And we're going to subtract that away from the 11,460 to get our age right there. So what is 11,460 minus 2,063? Shh, let everybody do it. Wait, let everybody do it. 11,460 years minus the 2,063 years from here to our sample. Shh, let everybody get a chance. They can't even put it in the calculator. Shh. Put your hand down. We're waiting. We're waiting. I'm glad you have it. We're waiting. We're letting everybody catch up. All right. You guys want me to blow your minds?
No.
Yes. All right. So we got 9,397 years using the fraction method. All right. Now, what is, you guys, I'm really tired of competing with you for volume, and you're talking over me still. The level of disrespect in here for yourselves, for me, and for each other is amazing. All right? So, we're going to compare using the fraction technique and see how close we can get using decimals. All right? So, somebody, please, divide 17 by 50.
0.34.
0.34? Okay. So we have 0.25 is a quarter, right?
Yep.
0.5 is a half. This certainly fits in right there. Agreed?
Yep.
So we're teaching. Remember yesterday I said I'd teach you the decimal method, right? This is it. Yesterday my hair, my brain, whatever was, yeah, my hair was on fire too. That's why there's some of this gone. So this is still going to be 5,730. This is still going to be 11,460. Okay? Now, from here we can kind of decide how precise we want to be. Okay? I don't want to have to divide this by a huge number, all right? So, watch this. What if I wanted to do, let's see, I'm just thinking out loud, 0.3, 0.35, 0.4, 0.45. And I'd be dividing by 1, 2, 3, 4, 5. So I've got my 5,730 years divided by 5. Somebody do that for me. What is it? 1,146. So each of these chunks of time is 1,146 years. Follow me? Look how close our decimal is to 0.35. Very close. Let's just find what it would be if it was at 0.35 and compare it to our age there. All right, see how close we get. So we're going to divide it. We got that. And we're 2 away. So 1146 times 2. Somebody do that for me.
2,292.
So 2,292 from here to here. So we're going to subtract, we're going to say 11,460 divided, oops, not divided by, excuse me, minus the amount of time back to our sample. So it would be minus 2,292.
9,168.
It's not exact, but it's close. And remember, we know it's a little bit to this side, so it would be a little higher. So we use two different methods to get pretty darn close to the age of the sample. Did you guys see what we did there? So we've used two different methods, and we got pretty darn close, and we know it would be a little more than that because 0.34 is that side of 0.35. So that should give you some kind of like, okay, we did it right. All right. Any questions on carbon 14 to nitrogen 14 decay series dating? All right.